Hello everyone, myself Madhuri Modak, Assistant Professor in Mathematics, Department of Computer Science, Abhidayanangar Senior College. In the subject Mathematics, Groups and Coding Theory is very important paper. Now in Groups and Coding Theory, already we have seen the first unit. Now we start with the second unit, that is groups, is multiplication. Now, till now, we have seen many examples of groups like Z, Q, R with respect to addition, some are with respect to multiplication, then matrices. But all these sets are infinite sets. So, we have not seen any finite group. Now, to show that certain finite set is a group, we need to prepare the composition table or Cayley table, because if we prepare the composition table, then it is easy to check whether that set is a group or not. So before going to finite group, first we see what is the meaning of composition table or Cayley table. A binary operation on a finite set can be defined by means of a table called as composition table or Cayley table. In fact, it is the best way of describing a binary operation on small sets. So if I consider G as A1, A2, An with binary operations star, then see how to prepare composition table. So all the elements of G we write as first row A1, A2, A3 up to An. Similarly, we write first column as all members of G A1, A2, An. And at the intersection, we write the binary operation defined on G. Now, to check for binary operation, actually we need to find ai star aj for all I and j. So here whatever is the answer of a1 star a1, we write it here. Then a1 star a2 we write in the a row of a1 and in the column of a2. Similarly, this will be a1 star ai, a1 star aj, and this is a1 star an. Similarly, in the row of A2, we write A2 star A1, then A2 star A2, A2 star AJ, A2 star N. In general, ith row element is AI and zth column element is AJ. So, by definition of star, we write it as AI star AJ at the intersection of ith row and zth column. So, in this way, we find all possible products AI star AJ. First row is called as heading row and first column is called as heading column. And AI star AJ is the entry at the intersection of ith row and jth column. Now, just to check whether it is a binary operation, see all the elements of that composition table. If all elements are from the set G only, then it is a binary operation. But if we are getting answer as different element from G, then it is not a binary operation. Now see, this is a finite set G equal to 1 minus 1 I minus I. So it is a subset of complex number set. We have to show it is a group under complex multiplication. Now, here if you observe set G, it contains only 4 elements. So, it is a finite set. Now, to show that it is a group, first we prepare the composition or Cayley table. So, we write members of G1 minus 1 I minus I as a heading row and heading column. And operation here is multiplication. So, we write it here. Now do all possible multiplication. So 1 into 1 is 1, 1 into minus 1, 1 into I, 1 into minus I. Similarly, multiplying all elements by minus 1 into 1, minus 1 into minus 1, 1, minus 1 into I, minus 1 into minus I, plus I. In this way, we get all possible products. Now we check all the properties of group one by one. Now first is binary operation. So binary operation is nothing but for any two elements of G, their multiplication is again an element of G. So in this table, we have calculated all the products. Now observe that 1 minus 1 I minus I, these are the only answers. So all entries of composition table are from set G only. So multiplication is binary operation on G. Now second is associativity. Actually in set of complex numbers, multiplication is associative and G is a subset of complex number set. Now, whenever associativity holds in superset, then obviously it holds in subset also. So, not necessary to prove associativity separately. Directly, we can say that multiplication in G is associative. Now, in case of finite set, how to find a identity element? So, actual definition is A star E is equal to E star A is equal to A. That means if we are multiplying E by some element A from left as well as right side, then we get again the element A itself. So, such element is the identity. So, using the same definition, how to identify identity element in case of finite set? Now it is very easy. Just observe the table. Now which row is identical to the heading row here? So the first row 1 minus 1 I minus I is matching to heading row. The corresponding element is 1. It means if we are multiplying all elements by 1 from left side, we are getting the same elements. Similarly, see this heading column. Which column exactly matches with heading column? It is the column corresponding to 1. It means for all elements, if we multiply by 1 from right side, we are getting the same element. So, just here to check the a row which is identical to the heading row and a column which is identical to the heading column. The corresponding entry is nothing but the identity element. So here one is the identity element. Now again from table we find inverse of every element, because as the set is finite set, it is easy to find inverse of every element separately. Now one is the identity element. So to find inverse of every element, in that row, we check where identity is present, and the corresponding element in the heading column will be its inverse. So for 1 is present here. The corresponding heading column element, heading row element is 1. So inverse of 1 is 1. Then for minus 1, in the row of minus 1 is appearing here. The corresponding heading row element is minus 1. So inverse of minus 1 is minus 1. Now for I, one identity is here. So corresponding heading row element is minus I. So inverse of I is minus I. In the row of minus I, one is here. Corresponding heading row element is I. So minus I inverse is I. Thus, for every element in G, we got multiplicative inverse. Thus, binary operation, associative, identity inverse, all properties are satisfied by G. Hence, we can say that G is a group under complex multiplication. Now, next is set of residue classes modulo n. Now, in previous unit, already we have seen residue classes modulo n. So congruence modulo n, this relation is an equivalence relation. So there are exactly n distinct equivalence classes which are called as residue classes modulo n. So the members of this class are Zn equal to 0 bar, 1 bar, 2 bar up to n minus 1 bar. Now on this set Zn we define binary operations addition and multiplication as follows. A bar, B bar belonging to Zn. A bar plus B bar is A plus B bar. That is the least non-negative integer obtained as remainder when A plus B is divided by n. So whenever we want to find A bar plus B bar, first we calculate A plus B and then we divide it by n, and whatever is the remainder answer, that is nothing but A bar plus B bar. Similarly, A bar into B bar is A into B bar, that is the least positive integer obtained as remainder when A into B is divided by n. So these two operations are very important on Zn. The operations addition modulo n and multiplication modulo n are denoted by these two symbols respectively. Now show that Z5, which is residue classes modulo 5, which contains 0 bar, 1 bar, 2 bar, 3 bar, 4 bar. It is a group with respect to addition modulo 5. Or the question can be asked as show that Z5 with addition modulo 5 is a group. Now as there are only 5 elements in Z5, it is a finite set. So we use again composition table to show that Z5 is a group. So prepare composition table. Now in first row we write elements of Z5 which are 0 bar, 1 bar, 2 bar, 3 bar, 4 bar. Similarly, in the heading column, we write a same element, and here the operation addition modulo 5. Now add 0 bar in every element of heading row. We get a same elements. Then 1 bar plus 0 bar, 1 bar. 1 bar plus 1 bar it is 2 bar. 1 bar plus 2 bar it is 3 bar. Similarly, 3 bar plus 3 bar it is 6 bar. But if I divide 6 by 5, then we get 1 as remainder. So instead of writing the answer of 3 bar plus 3 bar as 6 bar, we write it as 1 bar. Similarly, 3 bar plus 4 bar. Actually, it is 3 plus 4, that is 7 bar. But if we divide 7 by 5, we get 2 as the remainder. So answer of 3 bar plus 4 bar is equal to 2 bar. So in this way, we have to complete the table. Now the remaining properties are similar to previous example. If you observe all the entries of the table, then all are from Z5 only. So Z addition modulo 5 is a binary operation on Z5. Now addition modulo 5 is associative in Z5. Now observe this heading row matches exactly with this row. So the corresponding heading column element is 0. Similarly, this column matches with this column. The corresponding heading row element is 0 bar. So 0 bar is the identity element. Now in every row, find where 0 bar is appearing. The corresponding element in heading row will be inverse of that element. So for 0 bar, inverse is 0 bar. For 1 bar, 0 bar is here. So corresponding element 4 bar is its inverse. For 2 bar, here we are getting 0 bar. Corresponding heading row is element is 3 bar. So inverse of 2 bar is 3 bar. Similarly, for 3 bar, inverse is 2 bar, and for 4 bar, the inverse is 1 bar. So we got inverse for every element. Hence, Z5 is a group with respect to addition modulo 5. Now, multiplication modulo n. Now, here we are considering one set S equal to Un, which contains x in Z such that 1 less than or equal to x less than or equal to n, and GCD of x and n is equal to 1. So actually S equal to Un, it contains the integers from 1 to n such that GCD of x and n is 1. Means all the integers from 1 to n which are relatively prime to n. Now on this set we are defining star as a star b is the least positive integer obtained as remainder when a into b is divided by n for two elements a b in S. This is called multiplication modulo n. Then under this operation un is a group. Now this is one important theorem that an element a in Z has multiplicative inverse modulo n if and only if a and n are relatively prime. Now for this set particularly, we have to show that U10 is a group under multiplication modulo 10. Now here we have taken particular value of n as 10. So by using definition of UN, U10 contains x in Z such that 1 less than or equal to x less than or equal to 10 and GCD of x and 10 is equal to 1. It means U10 contains the integers from 1 to 10 with GCD with 10 is 1. Now start with 1. GCD of 1 and 10 is 1. So it contains 1. Next is 2. GCD of 2 and 10 is 2, which is not 1. So 2 is not present in U10. Next is 3. GCD of 3 and 10 is 1. So 3 is present here. Again, if you observe 4, 6, 8 and 10, all are even numbers. So the GCD with 10 is not 1 because they have 2 as a common divisor. So 4, 6, 8, 10 are not present in U10. Now 5. GCD of 5, 10 is 5, which is not 1. So again 5 is absent. Next for 7 and 9, their GCD with 10 is 1. So U10 contains 1, 3, 7, 9. As again it is a finite set, we prepare composition table by considering 1, 3, 7, 9 as heading row and 1379 as heading column. Now we do the multiplication. 1 into 1 as 1, 1 into 3, 3, 1 into 7, 7, 1 into 9, 9. Same way we prepare the table. Now again observe the elements of this composition table. All entries are from U10 only. So multiplication modulo 10 is a binary operation on U10. Now multiplication modulo n is always associative. So this is also associative in U10. Now heading row is identical to this row, so the corresponding element is 1. Similarly, heading column is identical with this column. Corresponding element of heading row is 1. So 1 is the identity element. Now to find inverse for every element. Now in the row of 1, 1 is appearing here. So corresponding heading row element 1 is its inverse. For 3, 1 appears here. Corresponding heading row element is 7. So inverse of 3 is 7. So inverse of 7 is 3. And for 9, 1 is appearing here. So corresponding element is 9. So inverse of 9 is 9. So in this way we got inverse for every element. Hence all the properties are satisfied. So U10 is a group with respect to multiplication modulo 10. Now next example, show that 1, 2, 3 under multiplication modulo 4 is not a group, but 1, 2, 3, 4 under multiplication modulo 5 is a group. Now the first set is 1, 2, 3 is a finite set. So again we prepare composition table. So here 2 into 2 is 4. But 4 modulo 4 means after dividing 4 by 4 we get 0 as the remainder. So 2 into 2 is 0. But 0 is not present in set 1, 2, 3. So binary operation, that property is not satisfied here. Hence we are not checking the remaining properties of group as the first property fails. Hence A is not a group under multiplication modulo 4. Now for second, B is 1, 2, 3, 4, 5, which is nothing but U5 because all these are in between 1 to 5 which are relatively prime to 5. Now similar to U10, we can show that U5 is again a group. The procedure is same. Now next is show that a set G is equal to 1 omega omega square, where omega is an imaginary cube root of unity, is a group with respect to multiplication. Now this is quite different. So omega is an imaginary cube root of unity. It means what? Omega raised to 3 is equal to 1. So omega is nothing but cube root of unity means cube root of 1. So remember omega raised to 3, that answer is always 1. Now to show that G is a group, again we prepare composition table. So 1 omega omega square in row and in column. Now 1 into 1 is 1. 1 into omega is omega. 1 into omega square is omega square. Now omega into omega is omega square. Omega into omega square is omega cube. But omega cube is 1 as it is a cube root of unity. Similarly, omega square into omega square is omega raised to 4. But omega raised to 4 is omega cube into omega. And omega cube is 1. So 1 into omega is omega. So finally we get omega square into omega square answer as omega. Now this is our table. Now again all the members of this table are from G only. So G is a group with respect to multiplication. Now, all these are complex numbers, and in complex numbers, multiplication is associative. So, multiplication in G is associative. Now, identity element. Again, by observing table, 1 is the identity element. And from table, inverse of 1 is 1. Inverse of omega is omega square. And inverse of omega square is omega. So, every element in G has inverse with respect to multiplication. So, G is a group with respect to multiplication. Thank you.